All right, who here knows anything about weather? A couple of guys, right? Who here is instrument rated? All right, we're going to talk about some stuff here that almost got me killed. So I'm a cancer surgeon by trade, right? So I'm not a professional pilot. I'm not a CFI. But what I am is a private pilot just like all of y'all. Back in 1983, there was a physician that loaded his pregnant wife and 2 young baby girls on his airplane. It was a Rockwell Commander in Panama City, Florida, and took off, headed back to home in Tuscaloosa because he was on call the next day. And he got into towering cumulus thunderstorms and ripped the wings off his plane. And the entire family fell from 8,000 feet and died. And they found him in the back seat with his arms around his baby girls. Okay? That doctor and that pregnant wife was my cousin. Right? Muff, right? So from the time I started flying, my family insisted that I do things safely and with great respect for weather. So what did I do? 37 years later, I loaded my family in my Cherokee 6 and promptly flew it into a thunderstorm trying to get to Destin. Did we need to be there? No. I just wanted to show off how fun it was to fly to the beach rather than drive 8 hours, right? So, from that moment on, I said, I'm going to learn about weather so I don't do that again. So what are the dangers from a weather perspective to pilots? I would argue it's visibility, it's icing, and it's thunderstorms and convective activity. So we're going to talk about some ways to identify some of those things. Who here has seen a Skew T chart? Can't figure it out, right? You're like that monkey in the pilot seat there, right? Yep. So this is typically what it looks like, and I'm going to go through some examples from the NOAA, the NOAA version, and I'll tell you how we're going to have to go away from that shortly. But it's the easiest one to interpret from a learning standpoint. So when I first saw this chart, my head did this, right? That's what everybody sees when they see these charts and all these numbers, right? But we're going to talk about how to really easy interpret this. So any of these charts, if you look at the bottom portion of the graph, what is highlighted in red there, that is always going to be temperature, right? It may be in Fahrenheit, it may be in Celsius, but that will be temperature, okay? And you can see here, you've got negative 20 Celsius, 0 Celsius, 20, 40, whatever. And I'll tell you about all those lines in a minute. On the left side, what's highlighted in gray, that is always going to be pressure. What is the millibar pressure at sea level?
1013.
Right? What?
1013.
1013, thank you, right? So right down here, right? Now some of these charts you'll have to convert the millibars into altitude, and we'll talk about that in a minute. In this particular version, they actually give it to you on the right side in feet. Some of the charts will do meters. In general, 1013 being sea level, 5,000 feet is going to be around 850 millibars, right? 10,000 feet is going to be around 700, and 15,000 feet is somewhere around 560 or so, okay? What these charts are describing is a theoretical event, right? If we take a parcel, just an imaginary pocket of air on the ground, and we heat it, what is that parcel of air going to do? It's going to rise, right? As it rises, it's going to do what? It's going to expand, right? Everybody's seen the balloons going up, right? The weather balloons. And likewise, the converse is the same thing. So if we push it down, it's going to heat up and it's going to contract, right? Now, there are weather balloons that make actual readings of the temperature and dew point as it goes up into the atmosphere, and that's partially where some of this data comes from. But most of these QT charts are actually model-derived data that is put into a graphical format so that you can understand it, okay? Now, the rightmost line on these charts is going to be the temperature, and that's the temperature as that imaginary parcel of air is rising up from the ground into the atmosphere, okay? On the left side, that is going to be the dew point. Sir, what is dew point? Exactly, right? So that blue line is going to be your dew point. So we're comparing the actual temperature versus the dew point at all of these.
That wasn't set up. I don't know where that answer came from.
We're going to compare the actual temperature and the dew point at altitudes as it goes up into the atmosphere. Now, why is it called a skew T? That's a weird name, right? Well, if we had the temperature in vertical lines like makes sense, then all these temperature dew points head off to the left and it makes it hard to interpret. So all they did is they just rotate the whole graph to the right, and that's why it's called a skew T. That's all it means. Skew temperature, right? Now, for areas that are to the left and up of that 0 degrees Celsius line, that is going to be freezing, right? Because the air that is less than 0 degrees is freezing temperatures, right? Okay. Again, here is your altitudes correlating with your millibars, right? So as you go up in altitude, 1,000, 5,000, 10,000, 15,000, you're going to see the changes. Now, we're going to start talking about these other squiggly lines that are on there, and I don't want you to get confused. This first red line that's kind of a slight curve has a fancy name called moist adiabatic lapse rate. All that is the behavior of a completely saturated parcel of air. So a 100% humidity parcel of air at the ground. What is that going to do as it rises, right? It has the ability to give away some of its latent energy by releasing some of the moisture into clouds, right? So it's not going to cool off as fast as it would as if it did not have that moisture. Right? 1.5 degrees Celsius. Who heard about that 2 degrees Celsius per 1,000 foot rule? Didn't y'all hear about that in private training, right? Yeah, I did. Where does that come from? There's no 2 degrees Celsius per 1,000 feet. Where it comes from is this. The dry adiabatic rate, that is a parcel of completely dry air. And as you can see, it cannot give off any energy from moisture, so it's going to cool off a lot faster at a rate of about 3 degrees Celsius per 1,000. So that 2 degrees that they taught you in private training, that was just an average, right? But the atmosphere never actually behaves like that, okay? Now, on the right side, you're going to see the winds aloft. And this is your traditional barb arrow depiction that you've seen on all the maps before. And it'll have the direction there. And then also what you will see is the scale will give a wind speed to the right. So you can see how your winds are changing from the ground as you move up into the atmosphere. Right? So that's all that right side of the graph is. Now, let's go back to our gentleman over here. You told me what the dew point was, right?
Don't ask me another question.
All right, I don't want to ask you. I'll ask your buddy here in the red shirt. If the temperature and the dew point are the same, what will we see? Visible moisture, right? Clouds, right? Clouds, fog, something like that, right? So on these graphs, where those 2 red and blue lines are overlapping, that is where you're going to have visible moisture. Now, if it completely overlaps, that's usually a very solid stratus type of cloud. It can be close to each other, but not completely overlapping. And in that area, you're going to see more of a broken or few layer of clouds, okay? Now, here's where we're going to start to see some interesting things with this graph. Somebody tell me where they think the cloud bases are on this graph. Exactly. So the very first intersection where the red-blue lines are meeting, that's going to be your cloud basis. Now you're saying, I don't need that information. I can get that from the weather report at the airport. Yeah, that's true. You can, right? So that's where your cloud bases are, and that's just where those 2 layers meet. But what do we all as pilots, especially instrument-rated pilots, want to know?
Tops.
Tops, right. Where do you think the tops are? Where they separate, exactly. So where those 2 lines diverge, that's going to be your tops. Now, I will caution you that that's only the case for a stratus layer, right? So you can get some towering cumulus and some of those puffy buildups that are going to puff up beyond that, and I'll show you those in a few minutes. But if you're flying along and you see that stratus like that, the top of that stratus layer is going to be where those 2 lines diverge, all right? And why is that important in flying? Usually we want to get above the tops of the stratus and then deviate around the cumulus buildups, right? Those are the rough things. So let's do some examples. We heard this morning about a temperature inversion. Now when I was training as a private pilot, I saw the word temperature inversion. I thought, what is that? We never see that, right? No, this is extremely common, right? As you go up in altitude, this red line is getting colder, and then all of a sudden it gets warmer as you go higher. So if you've got a warm layer capping off a colder layer below it, that is a temperature inversion, and that is very stable here, because that cannot, the rising air can't go any higher because it gets capped off by that. Now, what about this one? So, you sir, tell me where the cloud layer you think would be. Okay, that sounds good. All right, what do you think your conditions would be when you were flying in that? All right, and where are the temperatures? Yeah, how cold is it? Yeah, because that entire layer is below zero. Now that's not guaranteed to have icing. That's a whole different story. But there's definitely potential for icing there, right? This is the actual report from that area. Broken 5,000, overcast 6,500, so you were dead on, right? And then there were reports of icing higher up, So you'd need to be probably upwards of 15 to 17,000 feet to be able to top this and get above any icing, right? So what about this one? Jimmy? Yeah, so overcast was right around 900 feet. The tops were 2,000 to 3,000 feet. So this is an easy IFR day. You just pop right through it. It's above freezing. You're on top probably by the time you get into cruise. I don't know if everybody remembers this accident. It's been about 3 or 4 years ago. This was posted on the group. This was a PA32. He reported that he got lost into icing. And let's look and see what that looked like, right? So you've got continuous clouds from about 3,000 feet all the way up to roughly 11,000 feet here, okay? And most of that is below freezing, so you're icing. The problem in this case, the bases were 3,300, but the terrain was 3,000 feet. And he was topped out at 11,000 feet. He couldn't get above that, especially when he climbed into the icing. He didn't have enough power to get above that icing layer. So he was stuck. Had he looked at this chart before he took off, he would have either not flown or gone a different route or something like that, right? Yeah. So each of these is a prediction for a particular hour, and you can move that hour out. Yeah, I'll show you that in a little bit. All right, so here's another case. Where do you think the icing is going to be in this one? Yep, right around 5,000, 4,000 feet, somewhere in that range, right? Fairly thin layer, so you should be able to get on top of it if you had to, right? But where those two lines meet, all of that area is below freezing. All right, let's talk about convective activity now, because this will kill you. So what happens with convection? So the sun heats up moisture on the ground. It can be a lake, it can be a river, the ocean, it can be simply a moist farm field, but it's going to heat that moist air up, and that's going to rise. And it's going to keep rising as long as that air is warmer than the surrounding air, right? It's going to keep on going all the way up into the atmosphere until that air becomes the same temperature and density as the air around it, and that's where it's going to stop. All right? When we take that lifted air, and we can do it from the ground or from some other places, and we lift that artificially, that's called an air parcel line. And a lot of the apps will show you that in a purple line. All right? It can be from the ground, sometimes they'll lift it from the base of the clouds. The reason that line is important is because that air is going to keep rising until it meets the temperature of the surrounding air. Where that purple line crosses that red line is where that theoretically lifted moist air becomes the same density as the air around it, right? So that's your cumulus cloud that's going to start to lift up and burst out the top of your stratus layer, right? When you get that, you get vertical development. So air is rising. Rising air is what causes convective activity. Rising air is what leads to towering cumulus and eventually thunderstorms. Now, the difference in this area here is called the convective available potential energy. You may have heard the term CAPE. That is simply a term that is measuring that area between those two places. The more the difference is between that area, the higher the CAPE, the more energy is available for that stuff to keep lifting and lifting and lifting, right? Until you get 40, 50,000 foot thunderstorms. Now, most of the apps will have some place that you can read that out. A CAPE value less than of 0 is a stable air. Yes, sir. Yep. All right, so let's look at this again, right? So red line is what? Temperature, right? Red line is the actual temperature of the air, all right? This purple line is if I heated something up on the ground from the sun or whatever and let it go, it's gonna keep rising until that temperature equalizes with the actual temperature, right? So that's gonna keep going up. So that's where you get your convective activity, your thunderstorms. Does that explain it better? Anybody else have any questions about that? Yeah. It's a theoretical line. The purple line can be on the chart, depends on the app that you've got. Right. If you see it, it's usually labeled separately, and it'll be usually magenta, purple, stuff like that. Yes, sir.
The relationship there with the red line and the purple line, that area between it, is what we're looking at?
Yeah, the area between it, that's what is represented by this CAPE value.
And
The bigger it is, the more potential energy is available for everything to keep going up, right? So CAPE values of 0 are stable. CAPE values anywhere from 0 to 1,000 tend to start to get marginal. Above 1,000 into the 2,500 range is moderate instability. And then when you get above that, that's when you're talking about severe thunderstorms, right? That's a general guide, but not absolute. Yeah. No, the CAPE number is a number that is kind of like the area under this curve. Yeah, it's that. Now there's other people describe it with the difference in theta, which is simply just a lateral distance between those two lines at a particular altitude. But most places will use that integrated number to CAPE. If you see a graph that looks like this, where you have both temperature and dew point lines paralleling themselves up into the upper atmosphere, that's a fairly stable atmosphere, and it's going to generally be a very large-scale rain event, right? Because you've got moisture way up in here that's going to be condensing and falling. So if you see paralleling lines like that join each other way up in there, usually that's rain. Now, here's where the government has stuck us in the you-know-what the last week. Where to get the Skew Ts. I used this app, the Skew T Log Pro. Fabulous app. Unfortunately, that app and the Easy Weather Brief from Scott Dennistat was scraping information from the NOAA site where they got the ruck values and soundings and all that stuff. And that's where the initial graphs came from, was from this site. Fantastic app. Unfortunately, the government said you can no longer see that information anymore. Initially, they blamed it on a 508 thing about not being able to display alternate text, but the real reason is this was research information and was not meant to be used for operational use. And the fact that these companies were scraping the data and selling it in an app or a subscription, they felt like that was wrong, and they are not planning on reopening this site. But you can still get the data and you can still see these graphs in other places, and that's what we're going to talk about. One place is called Pivotal Weather, all right, pivotalweather.com. Nice site. There's a free version and there's a paid version, but you can click on regional, you can click on your area. If you click on a point, you'll get a sounding, okay? Unfortunately, they moved the sounding into the paid version of the app, but I'll tell you where you can get a free version. In this, it's the exact same graph that you just saw. It's just different colors. You still got the red line for your temperature. Now you've got your green line for your dew point. Your winds are on your right. You can pull up different models. So you can look at the NAM, you can look at the GFS, you can look at the the HRRR, which is the high resolution rapid refresh. You can pick a number of hours into the future. And you can look at all of those different things. And it also gave you the values of the CAPE on the bottom. Now in this one, it actually gives 4 different CAPE values. So someone was asking about where is that CAPE coming from. So there's a CAPE value if you lifted that air from the surface. There's a CAPE value if you artificially said, let's average out the bottom 1,000 feet of atmosphere and lift it from there. There's a forecast CAPE, which is another model. And then there's the worst case possibility CAPE, basically, this MU. But all of those will give different values, right? But here, same graph, red is your temperature. In this case, green is your dew point. You've still got your magenta. This is still that lifted line that we talked about where your CAPE is coming from. And you can see, because there's no difference between that and the temperature, your CAPE value is 0, right? Does that make sense? You still have your winds on the right. You have your millibars here. Unfortunately, they give the altitude in kilometers, and there's not really a way to interact with this chart. What I like to use is the Windy app. Who's seen Windy? Yeah, it's a really nice app. It's free for most of the good stuff on there. I do have the paid version. It's not very expensive. I think it's 20 bucks a year. But this is great because you can pull up a sounding and you can scroll across the bottom and watch how the sounding changes with the time. Right?
Where in the app do you get that?
Windy.com, and they also have an iPad and an iPhone app.
Right, I've been using it, but where do you get that?
I'm gonna show you. So if you click, and it's either a right click on a desktop, or I believe it's a 2-finger tap on your app, it'll pull up this box, and you'll have an area where you can pick sounding or distance and planning, show weather picker, forecast, whatever. If you click sounding, that takes you to the Skew T for that. You see it?
No, when I double click it just brings it in further.
Just click it once and it's in the top right corner.
Yeah, on the iPhone app, it's, hang on, I'll tell you, it is.
Found it, there it is.
You got it?
Yeah, thank you.
Top right corner, click once on the map and then it's...
Yeah, so tap once and it's in the top right corner. You may have to scroll over on the iPhone. On the desktop, it's a right click. Right? So you can expand that. And what I noticed the other day, because I hadn't really been using that for soundings until recently, is you can zoom in as you need to. You don't have the altitude markers, but if you will put your finger on the actual graph and scroll your finger up and down, it will give you a readout of the actual temperature and the altitude on the left, so you'll actually get the altitude. The other cool thing that I didn't notice until I started looking at this again, see this light and darker gray on the sidebar over here? Look at what's going on with your temperature and your dew point where that gray is. Right? So those are your cloud layers. So you've got a layer here, there's a clear layer in between, and you've got a layer above, right? And that's represented here. You've got the lines touching here, you've got a clear layer here, and the lines are merging here. So that's pretty neat. It makes it easy to look at. These are just different comparisons. So this is the NOAA example that we were talking about initially. This one's the easiest to learn from. These other ones are a little bit more hard to interpret, but it's what we're stuck with for now.
Is it for a particular spot on the map?
Yep, exactly. Nope, it's for when you put your finger on that windy spot on the map, it's giving you a forecast for that spot. Now that forecast is not, it's a computer generated forecast. And in Windy and in Pivotal Weather, you can pick which forecast model you want it to use, and you can even compare the different ones from the European the GFS, the NAM model, the HR rapid refresh model. You can compare all those and see the differences, but it's giving you a forecast for that one particular spot. Now, notice Wendy did not have the cape values on their Skew T, but it is there. If you go into the menu on the side, where they put the cape is they created a colored index, right? And you just click on that cape index, and then on the bottom of the screen, you can't see it on this picture, I didn't take a very good picture. On the bottom of the screen, it'll give the colors and the values of the cape that correspond to that. I did find a new site the other day. This is called twisterdata.com. And this one's also really easy to use online. It doesn't have a mobile app, but it's a really nice, easy to use app. You can again click on a spot. It gives you this QT. If you want the cape values, you have to go into the instability tab over there, and it'll give you the actual values there. So any questions so far on Skew T? Everybody knows how to use it now, right? Nod said. Yes, sir.
Many years ago, they had what they call a lifted index.
Yep, the lifted index is one of the measures that they have in there. So it's similar to CAPE and some of the other things. It's just another way of describing how unstable the atmosphere is. All right, let's talk a little bit about some in-flight resources to keep us safe, NEXRAD, air traffic control, etc. So, who's an air traffic controller in here? Anybody? Has anybody been to an air traffic control tower? Right? So they actually can depict weather on their screens. Now, all they're able to tell you is these terms on the right side, light, moderate, heavy, or extreme. And all that is doing is telling a readout of how strong the returns are. It doesn't tell them what's in it. It doesn't tell them thunderstorms or ice or snow or whatever. Just that's all they can read. And this is actually what it looks like on one of their screens on the left, right? The TRACONs, the approach centers, their radar is real time. They're getting real time feedback and they can give you real time weather. So if you're on flight following with a TRACON, you can ask them, they can actually give you accurate depictions of the weather and help you make decisions to deviate. Center controllers are using a version of NEXRAD, which is essentially what you're getting on your ADS-B or your Sirius XM, but a less of a time delay. They still have to have about a 3 to 5 minute build time where the NEXRAD radars put all of these images together and upload it to where everybody can see it. So there is a little bit of a delay from center, but that's what they get. Now, who here was told that Sirius XM weather was better than ADS-B? Okay, all right, we'll see. Isn't XM more detailed than ADS-B? I mean, after all, if I zoom out on my ADS-B, I'm getting all these blocky things like 200 miles away, right? Do I care what the weather is 250 miles away while I'm in flight? Probably not, right? If I make it that far, I probably should have done better flight planning on the ground to know what it's going to be. But if you zoom in, there's no difference in the actual depiction. The only difference between what XM and ADS-B is getting is they have a different color scale, okay? Who here has Garmin in their plane, right? And who has ForeFlight and their Garmin? Who has noticed a difference between the colors that ForeFlight displays on weather and the Garmin display on weather, right? And you're going, man, which one is right? They both are. Here's your legend. I encourage you to do this with all of your devices. Go into the manual, look up the color that's associated with the decibel return. I did this for the internet radar, the ADS-B radar, the XM radar that's displayed in ForeFlight. There's a 4-color version in ForeFlight and with Garmin, and I created this color chart. And basically, I put a mark at 35 decibels. I'm not flying at anything above 35 decibels, okay? In some apps, that's gonna be yellow. In some apps, there may still be a little bit of green, but you're not getting into the orange or red. But I encourage you to go through all of your apps and actually look at the decibel readouts, because the colors, although they're meaningful, they're not easy to translate over. Some people say, green takes the bugs off, yellow takes the paint off, red takes the wings off, right? That's not quite the case. Yeah, so in ForeFlight, you can turn on the map legend. At the bottom, you'll see the different colors, and it'll give you the decibel readouts on the bottom so that you can know what color is associated with what readout, okay? Now remember, in-flight radar is still a delay. Here's the accident from Texas years ago where the guy thought he was skirting around the cloud based on XM and actually ended up in it. That's what happened to me in my incident where I flew into the thunderstorm. I was trying to skirt around some buildups and in and out of towering cumulus and got myself into one of those. And you don't want to do that. Lightning detection. Yes, sir.
It tells you how old the data is.
It tells you how old the data was downloaded to the unit. It doesn't tell you the delay between the time it was scanned on the ground and uploaded to the satellite.
Okay.
So that timestamp is when your receiver picked it up.
Okay.
That's not when the actual radar scan happened.
That's eye-opening.
Right? The other thing to remember is when NexRad is building that picture, right? It scans once, maybe twice around at this level. Then it points the dish up a little bit, scans once, maybe twice around, points it up a little bit more, and it does that through, I don't know how many, 6 or 8 different azimuths. And then all of that is then put into a computer to generate that composite picture that then gets uploaded. So that's where some of that delay is. And then whatever time it takes before it actually gets to the satellite and gets down to your receiver. So you can have a delay, I've heard of up as long as 15 minutes. Lightning detection. So as clouds, this vertical development that we were talking about, as this stuff is rising up into the air, there's friction, right? And with that friction, you get a charge difference. And that charge difference, when it crosses over from a positive to negative or vice versa, is what creates lightning. Now you can have cloud to ground lightning, we all know what that is, right? But you can also have cloud to cloud lightning and also lightning discharges within a cloud, right? So ADSB, when it reports lightning on that, all it's reporting is cloud to ground only. My understanding, and I don't have XM weather, but my understanding is that XM weather gives you some cloud to cloud lightning reports. Can anybody confirm that? Y'all know? I think that's what it's doing. Now, these other devices like Storm Scope, Strike Finder, I've got one in my plane, Strike Finder, or Storm Scope rather. That is actually detecting almost like a radio would detect the discharges, right? And so you can actually pick up cloud-to-cloud discharges that is not enough to show up on your ADSB or XM weather. And if you're looking at some towery cumulus that you're thinking about flying through, and you're starting to see a little bit of lightning popping up on your storm scope, then that's one you want to deviate around if you weren't planning on doing that already. So although a lot of people took them out years ago because we were starting to get on board ADSB type weather and XM weather, I think it's a useful adjunct to help you know if some of these things are convective and starting to develop lightning versus just heavy rain. So one last thing we'll talk about, just because it was sort of informative to me. Anybody else look at this chart and have the immediate brain dump like I did? Like, I have no idea what they're talking about with this stuff, right? I'm like, what do all these squiggly lines mean? All that highs and lows. I mean, I know lows turn counterclockwise, highs turn clockwise. That's about the extent of what I got, right? And then I found this picture. And this puts it in 3 dimensions. And this started to really make sense. If you think about it, low is sucking air, right? It's low pressure. It's sucking air from around it into it like a funnel. That air rises. When it gets to the top, it spits it out into the upper atmosphere, which then feeds the high pressure next to it, right? That's then pushing the extra air going up into the upper atmosphere gets funneled by winds into an area of higher density that then starts to descend, and as it comes down, it starts to spin in an outward direction, and that's what we call a high pressure area. So if you think about, instead of thinking about lows and highs as independent structures, think about it as one complete system in a 3 dimension. And that's all I got. Questions? So everybody's ready to go out and conquer this QT weather right now. I hate that the government got rid of that site. It really was a great site. So Scott Denisat does a great program. He's got an app that he uses. I'm not a big fan of his app because it's an online web-based app called Easy Weather Brief. But he does a great job describing all of this, and I think he's planning on getting a different way of extracting some of this QT information. The data is still there. So Pivotal and Windy and some of these other apps are actually getting the actual model textual data from NOAA still, right? And then they've got their own in-house apps that are putting that into a graphical form. The pivotal one is actually powered by a program. It's a Python program that you can download for free called Sharpie. And you can put that on your computer, but there's not a mobile app version of that. So you could, if you really wanted to do that, I pulled it and put it on my computer, and it's sort of useful, but it's still not as good as the original NOAA app was. So, but I hate they got rid of it, but nobody was looking at the data, and I guess they didn't want people using it and selling it. Yes, sir?
Given that the SKUTs are modeled not from soundings and their forecasts, do you have any sense of how accurate they are? Or are there certain things that may be less accurate than other parts of that? Like conflict or things?
It depends on the model. And so that's why what's really nice, both in windy and pivotal weather, that you really could not do on the NOAA app, is you can actually go and you can pull different models. What I have found is the European model, which is ECWF or something like that, I think is how it's abbreviated in most of the apps. That one tends to be the most accurate for my flying. The GFS model is accurate on a wider scale, but not so much on localities. Same for the North American model, the NAM model. There is something called HRRR, which is the High Resolution Rapid Refresh model. And that gives very accurate information, but it's only good out for about 12 or 18 hours. But if you go to some of these other models, you can get some of these QT forecast up to 10, 14 days in the future. And that makes it nice because you're looking at a trip, you're like, I'm leaving today, but I'm gonna come back in 5 days. Is it gonna be icing when I come back in 5 days? Let me look at these different models and see if there's a potential for icing layers coming back. Yeah.
Well, I heard you say that I didn't hear you answer necessarily is the reality of what they're predicting showing up when you look around?
It's as good as any other weather forecast. So most of the time they're pretty good these days, especially with things like cloud layers. Those are pretty easy to forecast. Not so much the amount of convective activity necessarily, but they can predict there will be some convective activity fairly accurately. Yeah.
So, as I understand it, they are telling you what the potential is for cloud formation. They're not telling you.
Yeah, these are not actual readings. You can get actual radius on weather balloon readings, but the problem is that they are fairly scattered widely about. Like most states have like one place that releases a weather balloon, and they may release it twice a day if they think about it.
Have you read Buck's book,
Which one?
Weather Flying?
Yeah.
Is it worth it?
It's good. Any amount that you can read on this stuff is good. My problem with a lot of those apps, and it's kind of why the books is why I came up with this talk, is they're talking at a level up here. And they're talking in terms that I don't understand.
The whole thing was he's saying he dumbs it all down for a basic regular flyer, is what he's saying in the book. You didn't find it to be
I didn't know. I didn't think it was all that. Yeah. Okay. And the same for Scott's got a nice book, Weather Flying, and he's good about talking about systems and fronts and how that stuff interacts. But again, on a day-to-day basis, this is what I use. Yeah.
You got a book you'd recommend for someone who wants to do the IFR and the weather?
Actually, go to Scott Denistat's website. He does some paid courses and some webinar kind of things. And that's actually where I learned the most about this QT and some of these aspects. Like I said, the books that I've read they were either at too high of a level or they didn't go enough into how a general aviation pilot would use it. A lot of them are focused on airline pilot level and what is the ride going to be like at 30,000 feet kind of thing. Yeah, that's the one. Yeah, he's got a great website and lots of great articles and lots of great webinars. Yes, sir.
You showed the bases of the layer tops. Is there anything maybe listed on the SKUTs that will tell you any indication of the tops of the cumulative buildup?
So that's a very good question. Can you determine the tops of a cumulus buildup? All right, let's look at this. The problem is we know that the tops are going to be where the dew point and the temperature are the same, or diverge, right? Okay. The problem is with towering cumulus, what's inside of here is warmer than what's out here. And so it's going to keep rising until that air is no longer warmer than the actual air. So a theoretical top for this is where?
Where they match up.
What is that? Flight level 380, right? So that's where your theoretical top of this will be. Short of that, the only thing that's topping that cumulus is time. How long does it have to build, and how fast is it growing?
Like on a puffy summer afternoon, not likely thunderstorm, but just a way of telling where the tops of the puffy.
Exactly, you can't tell because that it's got energy, it's overshoot, right? It's just where the energy runs out. And that's kind of where that cape value plays a role, right? If you're seeing the little puffies, but the cape value is low, there's not enough energy for those puffies to grow very high, right? Or sometimes you'll see like there'll be a cape for here, but then there's like a capping layer, and then it won't go above that. Other questions?
So I thought at one time in the past, I thought there was a thing you could hit on your ForeFlight that said cloud tops, and now I can't ever find it anymore. Did it disappear?
Cloud tops is it is a new ADS-B output.
Okay.
But the problem with cloud tops is usually that's giving you this, right? If you've ever looked at it during widespread storms, the cloud tops they're reporting is like 350 or 330, and that's not helpful for us GA pilots, right? So the real cloud tops that we need is what's the top of the stratus, and then we're going to have to visually deviate around those other buildups. We're not going to top them.
I think they moved it though, because I can't find it easily. I swear I knew where it was.
FlyQ still has it. FlyQ, BFB, they still have it.
It may still be there, I just don't know where it is.
Yeah, I think it's an ADS-B derived product. So, but I'm not sure. Yeah.
And sometimes you could see it with Windy when you go through the profile view. You click on your spot, and then you go to meteorological, and then you can see the bottoms and the tops kind of graphically.
Yeah, Windy does have different aspects that you can pick: low cloud layer, low clouds, medium clouds, and high clouds, and tops, and you can pick those, and it'll kind of give you a rough estimate. And that's going to give you again either a true top of your thunderstorms, which is not useful, or if it's more of a stratus layer, it'll give you the tops of that. So yeah. Yes, sir.
So in short, knowing that you're spitballing a little bit, the cape helps you guesstimate.
Yeah, I'll tell you where a cape is fantastically useful, right? So if I wake up and I decide to go from Huntsville, Alabama to Destin on a summer day, right? And it's 10 o'clock in the morning, and there's not a cloud in the sky, and there's nothing on radar, right? But I look for a forecast at 1 o'clock in the afternoon, and the forecasted cape is 2,500, right? What am I going to expect by the time I get to Destin from Huntsville? Those little puffy clouds are going to be building up into some really nasty towering cumulus and probably some thunderstorms, because there's enough available energy for that to happen the later it goes through the day, even though there's nothing on radar now.
Yeah. So that's what ForeFlight's doing when it has the convective activity blocks that start showing up all over Florida when you're flying.
That's real stuff.
No, so there's convective forecasts.
Forecast, right? It says this area is juicy for.
Yeah. That's the weather forecaster sitting in his weather office saying, I'm looking at the cape, I'm looking at the weather, I'm looking at the conditions. That's why I'm putting a convective segment out, because there's a potential for that to develop.
Right.
Thank you guys for listening. I hope that was educational for y'all. So.
If you're not using Windy,